Biomedical Engineering from NIT Kurukshetra. Her research area is EEG signal processing and cognition and binaural beats carried out in collaboration with INMAS and DRDO. She has published 3 papers in reputed journals and represented her work in national and international conferences. After bachelor's, she has served her duties as a lecturer in Vaishno College of Engineering, Himachal Pradesh. She is currently working towards the application of biomedical signals for early detection of diabetic neuropathy, Parkinson's disease, and improving mental health through music and binaural beats. I would like Ms. Ritika Mahajan to take over and start the session. I request all members of the audience to mute their mic and put their queries in the chat box. All queries will be answered after the session. Thank you. You can take over, ma'am.
Okay, hello everyone. So, first of all, I would like to thank the person for a very nice introduction about myself. So, as you know that I'm Ritika Mahajan and I'm basically a researcher in the field of biomedical signal processing. So today I'm going to present my research area work and my views on the biomedical signal processing, basically the brain, cognition, and signal processing. So the summary of this webinar is to highlight how the signal processing can be applied to study the brain signals and basically the cognition. So I hope that you will enjoy this webinar and you will get a very good insight about the work and the signal processing application in this area. So let me start with the presentation. Okay. Is this visible to all?
Yes, ma'am. Your screen is
Okay.
visible.
Yeah. So EEG cognition and signal processing. So EEG stands for electroencephalogram and it is the brain signals that we detect, like your heart signals that are called ECG and the muscle signals that is called EMG. So cognition is basically a part of the brain study where we study how the brain actually works, how it recognizes the information, it ensembles the information and utilize this to make the decisions. So, but this is not an easy task. I mean, you can't extract this brain signals as it is and says, okay, the brain is doing this activity at this point of time and the other point of time it will do this activity, or you can't visualize the EEG signals as it is. This requires the signals to be processed in time domain, frequency domain, and to seize the correlation between the brain waves, and that is done with the help of signal processing. So before I switch to all these three terms, that is the neuroscience and the signal processing term, first of all, we should know what actually a signal is. So we all know that a signal is something that carries the information, and to extract this information, you need a system, and that system depends upon what kind of a signal it is, right? It can be a deterministic signal, it can be a random signal, it can be time variant signal, anything. So based on the basis of the type of the signal, your system is designed to extract that information. We live in a sea of signals. We are surrounded by various types of signals, from radar to sonar, from ECG to EMG to image. We all are surrounded with the multidimensional signals, unidimensional signals, and all these things. On the screen, you can see first there is an image that is basically a two-dimensional signal. It gives the information about the pixel intensity in and second is the sonar, and third is the ECG, that is the heart signal, where you can see the different waves, and all these waves have different significance, and it describes the different activities of the heart, and these are extracted by the with the help of ECG electrodes. And this is basically the electrical impulses that are being generated inside the heart, that helps in the contraction and the relaxation of the heart. And here it is the EMG signal, that is the muscular activity, where you can see there is a contraction and rest there is a relaxation. So you can see
Excuse
you
me, ma'am.
can't describe. Yeah.
Ma'am, your
Okay.
slideshow isn't uh, moving, ma'am. It's stuck at one slide.
Okay, which one?
It's at the first
Is
slide, ma'am.
this
The
now?
first.
Okay, let me check. I mean, uh,
Yeah, now it
now
changed.
it is. Now.
Yes, yes, ma'am. It's at slide 3.
Okay. Okay. So yeah, so I was presenting all these things. So yeah, so you can see on the screen where there are different types of the signals, and here it is the EMG signal, and here it is the ECG signal. Now, basically, there are three types of basic signals. That is the unit step signal, impulse signal, and the ramp signal. I think the people who have studied the signal processing and EC, they have gone through all these things. So I'm not going into depth. So this is just to give a brief idea what kind of signals actually we deal with. So another is deterministic and the random signal. So if you can determine the uh, or predict the next value of a signal, and predict the behavior of a signal with respect to time, like at the next instant of time what will be the characteristics of a signal, so that you can say it is a deterministic signal. But if you can't describe the you can't predict the next value of a signal, you termed it as a random signal. I mean, it's not determinable signal. If even a single characteristics of a signal cannot be determined at the next instant of time, we call it as a random signal. Next is a continuous signal or discrete time signal. So basically you can see the analog signals are basically the continuous time signals. I mean,
Sorry to interrupt, ma'am. Again, it
yeah.
is not changing.
Okay, it's not changing. I mean,
Ma'am, could
I
you switch to presentation mode or share your entire screen, ma'am?
yeah, I think I have to do that thing. Sorry. Okay, just a second. Uh, can you see it now?
Yes, ma'am.
Yes, ma'am. It's moving.
Okay. Yeah. So after going through the signals, I mean, now the thing is that okay, we know the signals, but how we are going to process it and how we are going to extract the information. So signal processing is basically a term of extracting and processing the information, and we apply various algorithms to modify the signals. Not only in the time domain field, we can also look the signal into the frequency domain field and the like spectral analysis, and into the correlation. What kind of how the two signals are being correlated. Is the signal is the first signal is negatively correlated with the second signal, or the positive there is some positive correlation, or there is no correlation at all. So three domains we study the signals, that is the time domain, frequency domain, and this correlation. So the application part is, now we know that signal processing can be applied to this satellite communication, radar, sonar, but now how it is utilized to study the biomedical signals. So we will focus on one signal, that is the EEG signal. So EEG signal is basically the neural activity of the brain. When our brain is processing some information, there is some change in the electrical activity of the neurons that are the cells of the brain, and this electrical change in the electrical activity can be extracted and used to study the and understand the activity that is going inside the brain. First of all, we should know that our brain has can be categorized into the three parts, that is the forebrain, midbrain, and the hindbrain. And this is the frontal part of the brain, this is the parietal, this is the occipital, and this is the temporal. Temporal part is basically related with the memory, the storage and retrieval, and the frontal part is basically to carry out the complex calculations part like focusing. So that is carried out with the frontal part. The visual system is basically handled by this occipital part, and the parietal part is more into the voluntary movements, like if you want to move from one place to another, so that is basically handled by the parietal part, that is the motor activities. So not only the motor activities is done by the voluntary and involuntary movements is done by the brain, but the information processing part is carried out by the brain itself. We don't know how we perceive information, how this information is being analyzed and uh, correlated with what we have earlier studied and makes out a decision. This all things is being studied under the cognition, the term cognition. So the cognition term is a set of processes that the brain use to achieve a particular goal. And these set of processes are perception, planning, attention, memory learning, language, reasoning, and decision making. For example, if you are visualizing this slide, okay, so you have studied brain in your primary education, and whenever when the slide with the brain diagram came to you, your brain automatically detect it as something that you have earlier seen. How it is that possible? How fast is that process, that the brain has seen that thing and it has retrieved the memory from the past, that okay, this is the diagram of the brain and we have studied in the primary education. How fast this process is going. And we have divided these parts into small small chunks and studied how the things are being perceived, planned, and then the decision is being carried out. These all things are being studied in the cognition. But how it is being studied? This is being studied with the help of EEG. So you can see on the slide, I think this is visible to all, right?
Yes, ma'am.
Yeah, so you can see how there is some lines drawn on the screen, and these lines are just like if someone has given pencil to a 3 months 3 years old child, and he has done something, he has tried to write something, right? So it's that chaotic. You can't see and you can't say okay, at this point of time the attention process was going on, at this point of the time the brain was making decision. So it's a very chaotic signal as it is. This signal has been extracted across 64 electrodes, and from frontal electrode to parietal electrode to occipital electrode. And visualizing this activity on single electrodes, you can see here how chaotic is this activity. Nothing can be predicted as it is. You can't determine what will be the activity in the next instant of time. So can we categorize this signal in terms of random signal? But this is not purely random signal. I mean, we can't categorize the EEG signal into a purely deterministic or a purely random signal, because if it is a purely deterministic signal, then you can easily determine the activity in the next instant of time. But if it is a purely random signal, then the brain will not be able to learn things. So we categorize this in a wide sense. I mean, we divide the EEG activity into small chunks, that is small windows, and in that windows we termed it as it is quite white sense stationary, quite stationary. So how this thing will go? First of all, we have extracted the raw signal. This is raw signal. Then we will process it with the help of filtering and other algorithms, and then the features will be extracted. Feature is like it can be in terms of the amplitude, it can be in terms of the power, it can be in terms of the bandwidth and frequency. Then we will select some features out of that uh, 10 or 20 features, and those features, selected features, will be given to a machine learning algorithm to classify it whatsoever be our requirement. Like if we want to look into whether a decision has been made or not, so it's a yes no part. So the feature extracted will be given to a machine learning algorithm, and it will decide whether the decision was made or not. So that is a classification part. So you can see how this cap is being weared. So here a person is wearing this 64 EEG cap, and you can see the electrodes. So these electrodes are basically filled with the gel so that the resistance between the scalp and the electrodes is minimized. And after that, these signals are being taken, and here is amplifier that will amplify the signals, and this amplified signal will go into a screen, and the signals will look like this. Now this is the raw signal that has been extracted across the 64 electrodes. Now our work is to, first of all, to look uh, whether there is a noise, and the noise can be due to the environmental factors, noise can be due to this electrical interference, due to the power lines, due to jaw movements, eye blinks, heart rate movements, the movements of the hands, face, etc. So the basically we can restrict all these noise by making the individual to sit calm and not making much movements, like not making eye movements for a while, avoiding eating chewing gum and jaw movements, sitting in a relaxed position, so that these noise and these artifacts can be minimized. But still, there are some artifacts like the noise from the electrical interference, that is basically the 50 hertz noise, and the noise from the eye blinks. Here you can see this is the signal, and we can detect that there is an eye blink because the EEG signal is basically in the microvolt signals, like 100 microvolts. But if you detect any other signal greater than 100 microvolts with a peak in going in the positive direction then in the negative direction, it is likely that an eye blink has been made. So these eye blinks are not required because it will corrupt the signal because of its high amplitude, and these are termed as the noise in the EEG signal processing. So these are removed. And next you can see 50 hertz noise, how it has corrupted the signal. So this figure is showing this 50 hertz noise. So we remove this noise by passing this EEG signal, raw signal, from a band notch filter, that is a band reject filter, where it will notch around 50 hertz and rest signal is there. So 50 hertz noise is removed. So yeah, the basic step in the pre-processing is this filtering. So filtering is required because first of all we have to band limit the signal. We have to band limit it, whatever be the desired frequency content. For the EEG signals, there is we don't read the signal above 100 hertz. So basically, the signals that are present lies in the 70 hertz maximum, but we take a window of 100 hertz. So that is 1 hertz to 100 hertz. So we band limit the signal to 1 hertz to 100 hertz. For that, we use the band pass filter, and we reject the reject the 50 hertz noise, and for that we use the notch filter, that is the band stop filter. You can also use the low pass filter and high pass filter depending upon what is your requirement, which frequency you want to study. Basically, the brain has five frequencies: alpha, beta, gamma, delta, theta. If you are studying the sleep, you are sleep study, you are basically confined to a frequency up to alpha, that is up to 12 hertz or 18 hertz. So for that, you will use low pass filter, and low pass filter with a bandwidth of 1 hertz to 20 hertz maximum. But if you are studying the alert alertness of a person, so you are looking into the beta frequency, you are not looking into the low frequency content. So at that moment, you will use the high pass filter with a bandwidth of 20 hertz to 30 hertz, or 20 hertz to above. You can also read the gamma frequencies also. So filters are the first step. Filtering is the first step that we will use in the pre-processing step to band limit the signal, to remove the artifacts, and um, to visualize the frequency component. So for that, you need this filtering, but the filtering has to be done such that it follows the Nyquist criteria. So Nyquist criteria, I think we all know that the maximum frequency component should be greater than the Nyquist frequency component should be greater than the maximum frequency that you are visualizing. Like if you are visualizing 100 hertz, so the Nyquist frequency has to be greater than or equal to twice of this maximum frequency. But we generally take it to the fourth or fifth multiple of the maximum frequency that we are using in the practical scenario. So two types of the filters that are being used are the finite impulse response filter and the infinite impulse response filter. Both have their own benefits, both have their own drawbacks. So finite filter we use for the ERP studies, that is event related potential, where we looked into the amplitude and the phase of the signals. So yeah, we know that the in FIR filter, so the phase remains uh, there is some group delay, but the phase remains there is a linear phase. So linear phase is required because we don't want that there should be any disturbance with the phase of the signal, because if we want to study the if the signal is saying say the extracted signal is like that, it has to be in a positive phase. But if you have used the infinite impulse response and the phase has been changed, has been corrupted by the 20-degree or 30-degree, so there is no such result of that. So you have to be very precise what kind of a study you are carrying out and what is your requirement. So for the EEG signals, we confine to the finite impulse response filter, but you can find out papers where they have used the IR filter too, because the order for the IR filter is less as compared to the finite impulse response filter. But if you want to make want to use the linear phase, you don't want that the phase should be corrupted, you should go with the finite impulse response filter. Next is feature extraction. So after filtering, the next thing is that what kind of features you are going to extract, whether it's a time domain features or it's a frequency domain features. Like uh, for the time domain features, it's like whether you are looking into the amplitude with respect to time. For example, what is the amplitude of a particular signal at 20 milliseconds, at 30 milliseconds, something like that. Or you want to visualize what is the power and the frequency of the signal at 20 milliseconds. So that depends on whatever you are looking, you will go with that thing. Or if you are looking whether a signal is correlated with the signal at extracted at time t, or is there any relationship, or there is no such relationship, then you will go with the synchronicity. So for this time feature extraction, the basic thing that you should know is the use of the Fourier transform, because you are going to visualize the things from the time domain to the frequency domain. You can't see all those things in the time domain, so you should use the Fourier transform to find out what frequency components a signal is having, and what are your desired frequency components that you want to see and looked into. So breaking that time signal into the small chunks and visualizing what all the frequency components are there, you can better visualize that signal. You can see here there is some time series data, and we have divided this data into small parts, small duration, like 10 milliseconds, 1 second data. Basically we use the 1 second data, we divide it into 1 second, because within the 1 second we assume the electrical activity of the brain is quite stationary, not fully stationary but quite stationary. We can assume it being stationary, and we can apply all those signal processing things that we have studied to only the stationary thing. Otherwise we have to move into the non-parametric analysis. So for 1 second data, we have convoluted it with a window, um, and this has given the frequency versus time scenario, how the frequency components, what were the frequency components that were present at a particular interval of time. So this x-axis shows the time, and the y-axis shows the frequency components, and this whole thing we called it as a spectrogram. So basically the spectrogram uh, is for the is visualizing the time dependent frequency components using short time Fourier transform. So we have used the bank of narrow band filters that has been applied to the data, and assuming that the data has been stationary in that time interval, and uh, the power spectral density is being computed by magnitude square of this DFT. Okay, so whatsoever be the result of the DFT, that has been magnitude squared and has been averaged over the n intervals. And here you can visualize this power spectral density as a function of frequency and the time. So basically it's a three-dimensional signal because it is giving you the information about the time, frequency, and the power spectrum. What is the power at that particular instant of time, and at what frequency that power was there. So next is the feature classification. So the topo map has been drawn. After this there is a command in the toolbox, that is topo maps. You can visualize this in terms of this thing, where you can exactly see at what position the what power was there, and at what particular instant of time. Like here at the 300 milliseconds, between 300 to 500 milliseconds, the activity was like this. And it's ADHD. It's the ADHD person, that is hyperactivity. The individual who are suffering with the hyperactivity disorders, and these are the control ones that are normal individuals. So uh, 1 to 1 a comparison was analyzed for window of 200 to 500 milliseconds, and in the go and no go. So basically there was a game where you have to press the key whenever there was a go signal, and you have to restrict yourself from pressing the key whenever there was a no go signal. So here in this ADHD to people, you can see that there is some suppression of the activity. Okay, but it was highly the dominated in case of the control. So the normal individuals were better in controlling this activity, that is no go activity, rather than the ADHD. So these individuals find it difficult to control themselves, to restrict whenever there was a no go signal. And this was highlighted on the CZ electrode and the parietal electrode. So basically two electrodes were used to visualize this thing, that is the parietal electrode and the central electrode. And this is the these were the features that were visualized. So the features are basically the power spectrum at 300 to 500 milliseconds and at spatial location CZ. So these features, when being processed, extracted, and classified, can be used for the BCI application. Like uh, you can use the signals where you find the maximum amplitude, and to whenever the maximum amplitude has been find out, so the device will make a movement towards the right, and if the minimum activity has been find out, the device will make a movement to the left. So depending upon what is your requirement, you can utilize those features to uh, for the BCI application. For example, here in this ADHD student, so we find out that there is some suppression of the activity. I mean, the activity was not so dominant in case of the ADHD student. So whenever our device will find out that the activity was no, because the activity was normal in the go scenario, but it was different in the no go scenario. So we can classify individuals on the basis of this no go activity spectral content, whether the person is suffering from ADHD or not. So this is the medical application to uh, distinguish a person from suffering from some illness or not. So this is a brief introduction how signal processing can be utilized in the biomedical signal processing. And I would like to end this series, this webinar presentation with a short note that signal processing is an art, and it requires passion and consistency to become excellent in this thing.
Thank you, ma'am. Thank you for that amazing and informative session. Now we open the platform for any and all questions by the audience. I have a couple of questions myself that we received during registration, so I'll start with that. So the first question is it wise to use EEG in order to analyze dynamic functional connectivity states?
uh, Dynamic functional connectivity in what is the application, I mean, in what scenario you want to look.
Ma'am, the question is like this: is it wise to use EEG? Is it uh, accepted to use EEG in dynamic functional connectivity states?
Okay, I will take it as a functional connectivity scenario, because I am not okay. uh, okay, dynamic, I'm not getting into whether the person is looking into dynamic thing on the into the uh, real time thing, right? So basically we have used the EEG to find out the functional connectivity. I mean, so yeah, you can use it into the functional connectivity, but the thing is that you should uh, be very particular, because when you go into the depth of the functional connectivity, you have to deal with the source localization. Okay, so it is the inverse problem. Like you are looking into the EEG signal, and you are now inversing this problem that okay, the signal has come from this part of the brain. It's not like I have tell you that okay, we have extracted this signal from the CZ, right? Central electrode, the signal has been extracted. But whenever there is some activity that is going on in the brain, there are some layers, and crossing those layers, the signal is being extracted via the electrode. So there is some widening of the signals. Like the signal can come from the parietal region, but it has been spreaded to the occipital electrodes and some of the temporal electrodes too. So you can't say that okay, the signal if has been extracted from these particular electrodes, so that has come from this electrodes, this part of the brain only. No, it's not the scenario. So EEG can be used for the functional connectivity analysis, but that requires a very good signal processing algorithm. The algorithm that can deal with the spreading of the signals and the dynamic thing, and you can say basically uh, the randomness of the signal. So yeah.
Thank you, ma'am. We have another question in the chat box. Which headset is better for recording EEG and which works well?
Could you please repeat? Sorry.
Which headset is better for recording EEG and works well? It's in the chat box, ma'am.
Okay. So in market there are many companies that are providing you the headset. So Ant Neuro is one of them. We have worked with the Ant Neuro and it was really good. I mean, it comes with their software also. If you don't want to do the signal processing by your hands, you can utilize their software also. And other also are present in the market. So few are, I can name you few, like Neurostar. I guess Neurostar is I didn't remember. I mean, Ant Neuro is the one that we have used, and it's really good. But the next thing is that what is your application? Like if you are looking into uh, the whole brain activity or to a particular part of activity, like there are 4 electrodes also there, 64 electrode system is there, 128 electrode system is there, 256 electrode system is there. So what is your application? That depends on which kind of headset you are going to use, but I will recommend Ant Neuro. I mean, because we have worked with this and it's quite good, comfortable to work with, and reliable. So I don't know about the other headsets because I haven't worked with that. We were working with the another headset, but that was 4 electrode system, and I didn't love. And our work was not confined to the 4 electrode system. So Ant Neuro comes with all these configurations, and now they have launched even the TDCS also, transcranial direct current stimulation. So yeah. Okay, so next question. How would one differentiate between the random spikes and noise artifacts if they do lie in the same range? Really good question. So basically, when you are working with the any kind of a signal, you should know uh, first thing, what is the signal and what is the noise. If you know the noise, what kind of a noise it is. I mean, basically, we deal with very general noise, and that is common to all signals, right? Like the electrical interference, we know 50 hertz electrical interference can come. So we should look into the frequency spectrum, whether you are getting some activity in the 50 hertz, and if that is the 50 hertz activity is there, so reject it. I mean, if because in the brain activity we have no such activity in the 50 hertz range as it is. We, I mean, 40 hertz is the gamma. So if you are looking into the gamma frequency, then you have to be very particular about that frequency. But if you are not looking to the gamma, if you are looking into only the 20 hertz frequency, you can neglect it. You can use a notch filter and just neglect it. Between the random spikes is that the it is for the short duration. These spikes are for the short duration, and with a very large amplitude. So you can just look into the signal and you will come to know, because EEG, in EEG there is no such activity that is above 100 microvolt, or you can take it to the 150 microvolt. If you are getting any activity that is above this thing, termed it as a noise. Yeah.
We
And
have another.
okay.
Continue, I'm sorry.
No, you can go on. Yeah.
Yeah, so we have another question. Where can we get a standard database for EEG signals with artifacts in it?
Mm, I You can look into the GitHub if someone has uploaded that data set there, or there are some sites uh, that deal with all these data set. I mean EEG data set. So one site is the mm, uh, okay. This okay this site is open to UCI, but it is the EEG data set. If you looked into the uh, uh, online, you will find out that there is some machine learning repository, so by the UCI. There you can also find the EEG data set, and if you are working with the EEG and ERP, so that is also available for the public download. And uh, Kaggle, the GitHubs, these all have some data set. I mean, people have you uploaded the data sets, and also with the algorithms, also with the functions they have used. I think if someone wants to start with that thing, these are the best place, because you can use their algorithms on this on the data set, and see how the features are being extracted and what kind of features are being extracted, because there the data set is uploaded with a very brief summary. But rest all place you should look into the data set has been cleaned or not. So personally I will recommend that go with the unclean data, don't go with the clean data, because most of the things that has been extracted from that data, I mean sometimes they have band limited the data to a particular frequency component. So yeah,
Thank you,
open
ma'am.
euro. Yeah, open euro is also there. Open euro, you can check it out. Open euro, that is also having public data sets with the results even, for different MRI, MEG, EEG.
Thank you, ma'am. There's also one particular source, physionet.org, as specified in the chat box by Mr. Sanish.
Yeah, I mean,
Uh,
okay, Physionet is also there. I mean, if you looked into the field trip or and neuro, I mean, those who are also dealing with this thing, they have also uploaded the data. The data is vast, and many organizations have uploaded the data. So yeah, that is also there.
yes, ma'am. So we have one final question. How
Okay.
neurotransmitters can influence an EEG signal?
Yeah, that is a very good question. Sorry, I skipped it. Okay, yeah. So basically the activity that you are looking into, this EEG activity, so this is not because of one neurotransmitter. I mean, if you are like you are uh, listening to this webinar and you are speaking, so at that particular instant of time the beta activity is going on. Beta activity in the sense, the frequency that is dominated inside my brain is in the beta frequency range, that is 20 hertz to 30 hertz frequency is dominated when I am speaking, actively participating in something, where the concentration and mindfulness is concentration is required, and alertness is required, focus is required, like doing mental calculations at that particular instant of time. If you are playing the video game, just like video games, the neurotransmitter dopamine is in the peak, where so that dopamine activity can influence the neural activity, like you have seen in the case of the Parkinson's disease patients, where the dopamine is not produced in the required amount of time, and they were not able to make the movements, right? So at that particular instant of time, if you apply electrode on the parietal region of that patient, you will get a decrease in the amplitude of the signal in beta frequency as compared to the control signal, right? So there is some change in the activity at the beta frequency, uh, because that beta frequency is related with the voluntary movements, and it is also related with the dopamine activity, right? So neurotransmitter can play a role in the uh, in varying the this synchronization desynchronization of the neural impulses, and the thing that you are extracting on the electrodes is basically all these activities. If a group of neurons are active are performing activities in a synchronized manner, you will get a large amplitude. But if there is some desynchronization, you will get a low amplitude or an amplitude in the negative direction with the negative phase, right? So these neurotransmitters are somewhere responsible for the amplitude and the phase of a signal that is being extracted on the electrode. So, what would study of EEG signal play a major role in the treatment of seizures, sudden neural condition like epilepsy are helpful mostly for the passive continu. Okay, basically the study of the epilepsy. Okay, yeah. So, epilepsy is different from cognition. Okay, so because in the cognition, you are studying the activity in the surface level, I can say. The activity has been originated in one part of the brain, and the rest part of the brain has been involved, and you are getting some activity. Because if you are thinking, so if you are visualizing something, that means you are not only perceiving that thing, the decision making part is also going on. So the whole brain is involved in the cognition part. But when you are studying the epilepsy, in that sense, or Parkinson, a particular part of the brain is involved, like in the Parkinson. So substantia nigra uh, is a place where the dopamine activity is reduced. So and basal ganglia, we study the basal ganglia. So for studying the Parkinson, we will confine ourselves to the study of the parietal region, right? So the activity from the parietal region that can be extracted and can be visualized to distinguish whether a patient is suffering from a Parkinson or some or not. uh, and treatment, for the treatment purpose, I will say, uh, yeah, it can be used for the treatment. But before that, you have to classify, you have to extract those features where you can say, okay, where that can be used to classify whether a particular event can be detected as a seizure or not. And if the particular event can be detected as a seizure, where that is the feature is saying that a seizure is detected, so that means whenever that EEG signal or that EEG signal will come, we can say that seizure has happened. And we can give the EEGs, for example, if the seizure activity is in the beta frequency range, we can give the uh, s- electrical impulses in the alpha frequency range to compensate all those things, right? But this is in the theoretical mode. We have to practically justify all these things, and this is in the experimental region. I think you have heard about the Neuralink, right? So they are also using the EEG activities, neural oscillations, to predict, to treat the disease, and they have given that in papers and hypothesis. But on the ground level, when it will come, it will take some time. I mean, it can take 2 or 3 years after the experiments being started. So yeah, you can use the EEG signals to detect and to treat the seizure. For example, if your mood is not good, so you can see, if mood is not good, what kind of activity is going on inside the brain. If it is going on in the theta range, you want to be in a good mood, neurofeedback the alpha frequency or beta frequency, so that your mood will shift to the excited level, right? So neurofeedback is the answer for the treatment of all these things.
Thank you, ma'am. Thank you for joining with us today and delivering this wonderful seminar. I think we can end the session here. I request you all to please fill the feedback form that is present in the chat box. Please click on the link and fill the feedback form. Thank you, guys. Have a great day.